welcome back. So this is assessment problem 4.18, and in this question the statement is that a voltmeter with an internal resistance of 100 kilo ohm is used to measure the voltage VAB in the circuit shown. Okay, so this is our circuit, and here a voltmeter is will be connected to find out the voltage here, which has the internal resistance of 100 kilo ohm. So what would be the voltage, what would be the reading of that voltmeter? Okay, so generally in this question we can easily connect our resistor here. Okay, and this is of 100 kilo ohm, and we can easily find out the value of this voltage by using any method. Okay, we can use to find out the voltage, this voltage, by using the mesh current method or node voltage method, or by using the source transformation method. Any method you can use here, and you will basically get the correct value of it if you are using any other method. But in order to find the effect of the load resistor here, we will see all the circuit here from point A and B, and we have to look at it and should have a circuit which will be composed of a single resistor RTH and a single voltage source, and this circuit is basically called the Thevenin's equivalent circuit. So in order to get the I can say that get the conceptual overview that what will happen if a 100 kilo ohm voltmeter is connected here, or the voltmeter of higher internal resistance is connected here, what would be the effect of the voltage reading which a voltmeter will be reading from these two terminals. Okay, so in order to grasp the conceptual overview of this problem, we first have to convert it into the Thevenin's equivalent circuit. Okay, so that's the reason I have been using the Thevenin equivalent circuit here. And after finding out the Thevenin equivalent circuit, I will analyze my circuit and see the effect of the internal resistance of the voltmeter. Okay, so in order to find the Thevenin's equivalent circuit, first of all we have to find the open circuit voltage, which is also called V0. So in order to find the open circuit voltage, this circuit is already open circuited, so I can use any method whatever I like. So in order to avoid any difficulty here, I can see here that this current source is shared between these two meshes, so I will generally use here the node voltage method. Okay, so when I will use node voltage method, let me call this one V1 and use this node, this overall node, as the reference node. Okay, so you can also use the same equivalent circuit which I used to draw in the questions related to the node voltage method, but I'm not deploying that here because of because I have to preserve the time for the other steps. So now in order to find the values here, I can see here that the currents, sorry, let me use that color. So the currents here are basically, let me call it I1, I2 and I3. Okay, so this current is basically following this way. Okay, because this is an open circuit, and these are the only branches which are left here. So now at node V1, what will happen? The values here will be V1 plus 36 divided by 12k. Okay, similarly this is the voltage, this is the current here which is in opposite direction as that of I2, so it would be minus 18 milliamps, and similarly here it would be plus V1 divided by 60k and this should be equal to 0. Okay, how come I get this equation? This is due to the same process I used earlier on by using the KCL at node 1. Okay, so after finding the values here, I will find out this equation. Okay, so now moving this 18 milli at the other side and finding the LCM here, what I will get here, I will get 60k as the LCM, and then multiplying both sides by this k. Okay, these two will cancel out. Similarly, this k will also make this milli 10 raised to power 0. So let me remove this k and milli here. So now this is now 60, so 12 60 is now 5, so 5 multiplied by all these terms will be 5v1 plus 5 multiplied by 36 is 180. Similarly, this term here, this will be v1. Okay, so now as these terms are simplified, this would be 6v1 plus 180 divided by 60 equal to 18. Now taking 6 common from this side, this would be v1 plus 30 divided by 60 equal to 18. Okay, so this would be 10 here, 10 multiplied by 180, it will be what, v1 plus 30 equal to 180, or the value of v1 will be 150. Okay, subtracting 30 from both sides, I will get here 150. So that is the value of v1, and I can clearly see here that the same value, as no current is flowing through 15 kilo ohm resistor, so that's why the voltage drop here is 0 volts. So that's why the value of VAB is also the value of v1. So here the value of v0 is equal to v1, which is equal to the 150 volts. Okay, so that is my voltage here. So in order to find the other quantity here, what I will have to do, I have to make this terminal as a short circuit. Okay, so let me make it a short circuit. When I will short circuit it, I can see here that the same node will be preserved here, because these two will remain the same, and now these three will be included as a second node. But now this resistor will also be included in my analysis. So let me again consider it as a reference node and using it as a my node here. Okay, so now let me call it v2. Okay, so in finding the other quantity here, I will call it v2, and I have to find out this short circuit current. Okay, this is the value I have to find out here from here. Okay, so now again using the node voltage method in order to find the short circuit current, again using the node voltage method, I can clearly see here that this is the current, this is the current, this is the current, and also the other current is this one. So let me call it I1, this is I2, this is I3, and this is I4. Okay, so according to the KCL, the summation of I1 plus I2 plus I3 and I4, this is equal to 0. Okay, so now putting their values here, the same values will be put it here, V2 plus 36 divided by 12k, and moving it to the other side. I will move it directly to the other side because it is of this is in opposite direction as that of I2. So I will directly move it to the other direction. So it will be 18 milli. Similarly, the value of I3 is here. I2 is moved to the other side. I3 is V2 divided by 60k. Similarly, it would be V2 divided by 15k. Okay, so now this is my equation. Again taking so this is k, again multiplying both sides by k, so this m will be cancelled out with this k, and these all kilos will also be cancelled out. So when I will take the LCM here, okay, so when I will take LCM here, when I will remove it, it will also remove, and when I will take LCM here, what will happen? The LCM here I will get is 60. Okay, so again multiplying 5 here inside, I will get 5v2 plus 180 plus v2, and here again 15, and this is 4v2, and this is equal to 18. Okay, so now it would become v2 v2 v2, so this will be 10v2 plus 180 divided by 60, this is equal to 18. Okay, so now I have this equation here, so let me move down, and when I will simplify it by taking 10 common from this side, it will become v2 plus 18 divided by 60, it will be 18 here, so this will cancel out. I will get here v2 plus 18, and 18 multiplied by 6 is 108. Okay, so this 6 multiplying both sides by 6 again, so I will get here 108, and similarly the value of v2 would be 108 minus 18, and so I will get here 90 volts. Okay, so that is the value of v2 here, which I have been finding in this circuit. So now in order to find the value of ISC, what should I do? I should have to divide the value of this voltage by this 15k, because ISC is the same current, which is I4. So now as ISC is equal to I4, and the value of I4 is how much? That is the V2 divided by 15k. Okay, so now the value of V2 is 19, this is 15k, so what I will get? I will get here 6 milliamps. Okay, and that is the value of ISC. So the value of ISC is also known here. The value of ISC is 6 milliampere, the value of V1 is 150 150 volts. So now in order to find the value of RTH, I know the value of RTH is V0 divided by ISC. So the value of V0 is 150, and the value of ISC is how much? That is 6 milliamperes. So what will I get? I will get here, multiplying it, I will get 6 12 6, I will get here 25 kilo ohm. Okay, so that is the value of RTH. So in order to now connect my voltage source here and a resistor here, okay, so now these are my terminals, terminal A, terminal B, and this is the resistor 25 kilo ohm, and this is the voltage, which is of 150 volts. So now this is the overall scenario, and here we are told that to connect a voltmeter which has the internal resistance, that we call it RIN, and and the value of this internal resistance is 100 kilo ohm. So now that is the scenario. As the internal resistance of this voltmeter is 100k, so now in order to find the voltage across it, okay, I can use any method, but let me use the voltage divider method. So in voltage divider method, I will deploy the resistor across which I want to find out the voltage, divided by the resistance is summation of the resistances in series multiplied by the source voltage. Okay, so in multiplying it, what I will get, 100 divided by 125 multiplied by 150. So after multiplying them, I will get here 120 volts. So that is the voltage which this multimeter is going to read. And you can also see here that if there is no load, the available voltage here would be 150 volt. But when a voltmeter of very high resistance is connected here, you can also see the effect of the internal resistances which are connected here, and so the voltage drop here, which is dropped because of the overall effect or the loading effect here, that is the 120 volts. So that is the effect. If you will reduce the value of this resistance, you will clearly see the voltage drop here will also reduce. So okay, so that is also because of the loading effect. So in order to make it same as that of this current, we have to make this resistance infinite, and in order to make it, is very difficult for us to make it infinite. Okay, so then we use some source transformation method, or another method which is the decoupling method, by using the transformer or the common collector configuration, or another device we have is the operation amplifier, which shows these two terminals as the infinite input resistance. But that is the deception which this resistor will see, because we have to measure the same voltage which is available at the input end. And so that is the end of this question. And you can clearly see here that here we used some very lengthy method, despite using some very easy methods, which are basically the mesh current method and the node voltage method. But the usability of the Thevenin equivalent circuit has given us the overall performance of the circuit, and formulated a scenario in which we can connect any resistor across these two terminals and see the effect of the voltage rise or drop across these two terminals. So thank you so much, and I hope you have grasped all the concepts related to the Thevenin and Norton theorem, and I will see you in the next video. Thank you so much.